You write a SQL query. The syntax is flawless. The red squiggles are gone. But when you deploy it to production, the system seizes up. It either returns an empty dataset or locks the database entirely. The root cause of this failure usually stems from a single habit. Developers treat SQL as if it were a standard procedural language, like Python or JavaScript. In a procedural language, you write step-by-step instructions dictating exactly how a task is executed. SQL is declarative. You write what you want the final output to look like, and the database engine determines the execution path. Under the hood, it doesn't use standard programming logic. It relies on a mathematical framework called relational algebra to retrieve and organize datasets. This flowchart introduces the SQL logical execution pipeline. The engine processes commands chronologically, from, where, group by, having, and select. You read queries top to bottom, but the hardware follows this sequential pipeline. Ignoring this order creates invisible errors. When you apply procedural logic to a pipeline built on relational algebra, the result is code that compiles perfectly, but returns data that does not match the original intent. Here are 5 ways that disconnect happens. In any standard programming language, a variable evaluated against itself is an absolute truth. X equals X always evaluates to true. On the left of this split screen, a common query attempts to find records with missing data using where status equals null. On the right, we have a logic gate waiting to evaluate it. In SQL, null does not mean an empty string or a 0. It literally represents an unknown or missing piece of information. If 2 pieces of data are entirely unknown, they cannot be definitively equal. This truth table illustrates how SQL handles the ambiguity. Instead of standard Boolean logic, it uses 3-valued logic: true, false, and unknown. Because null represents missing information, evaluating null equals null resolves strictly to unknown. This creates a mechanical problem in the pipeline. The where clause has a rigid constraint. It only allows rows that evaluate strictly to true to pass to the next node. When the engine hits an unknown result, it doesn't throw a syntax error or a warning. It simply discards those rows entirely. To fix this, you must use a specific binary check. Operators like isNull or isNotNull force the engine to evaluate the missing data as a strict true or false. Failing to use isNull forces the engine to discard missing datasets without ever triggering an alert. Moving to the very first stage of the pipeline, the from clause. When you write a left join, your intent is to merge 2 tables while preserving every single record from the primary, left-hand table. A common developer trap occurs when you write that left join, but apply a specific filter to the right-hand table later in the where clause. This Venn diagram shows the first mechanical step. The left join successfully merges the tables. The left circle retains its full shape, and any empty intersection slots from the right table are filled by padding them with null blocks. But watch the execution order. The where clause runs after this join is complete. It scans and evaluates this newly unified null-padded dataset. If your where clause filters for a specific string, like checking if the status is completed, it runs into those padded null blocks. Evaluating null against the string completed triggers the 3-valued logic rule, resulting in unknown. As a result, the engine discards the null-padded rows, removing the very records the left join was designed to preserve. Mechanically, filtering the right-hand table in the where clause morphs your left join into an inner join. To maintain the join's structure, constraints targeting the right-hand table must be placed inside the on clause rather than the where clause. Placing constraints in the wrong chronological stage of the pipeline alters the underlying relational algebra, which can lead to incomplete datasets. This animated diagram reestablishes the full logical execution pipeline. Look specifically at the middle 3 nodes: where, group by, and having. A common misconception is that where is strictly for filtering individual rows and having is strictly for groups. This perspective focuses on syntax, but misses the engine's internal execution architecture. If you place a standard row filter inside the having clause, you force the engine to load the entire unfiltered raw dataset into memory first, moving it all through the group by stage. To do this, the engine creates aggregation buckets. It makes memory allocations to group the data and calculate metrics, only for the having clause to discard those buckets moments later. Contrast this with the where path. The where node executes before memory is allocated for groups, meaning it processes the data when the set is much smaller. Efficient querying requires aggressive pruning. You must drop the maximum number of rows via the where clause to minimize the workload before it ever reaches the group by stage. Treating having as a standard filter consumes hardware, compute, and memory on data that the engine will never include in the final output. Another habit that impacts memory usage is using group by and distinct interchangeably when the only goal is to deduplicate a list. This split screen shows the physical difference. On the left side, distinct performs a lightweight set-based operation. It executes a fast hash deduplication pass where identical rows merge instantly upon hitting a hash table. On the right side, the group by command executes a different engine task entirely. Group by provisions database memory space to build buckets, specifically preparing to calculate mathematical metrics like sum or count. If your only goal is to remove duplicates, allocating space for these aggregation buckets is an unnecessary use of hardware resources. Utilizing group by without an aggregate function increases memory allocation for mathematical preparation that never occurs. Modern query optimizers are highly advanced, leading to the assumption that they automatically flatten and fix all inefficient subqueries. That an optimizer cannot always fix a correlated subquery. This query type evades flattening because the inner query relies directly on dynamic variables from the outer query. This execution plan visualizes the resulting nested loop algorithm. An outer loop pointer takes a single step on the main table, which triggers a full scan of the inner subquery table. The scaling here is quadratic. If you have 100,000 users in the outer table, the database may execute the inner subquery 100,000 separate times, potentially totaling 10 billion operations. Compare that loop to an efficient hash join, where both tables are scanned into memory sets exactly once, operating in linear time. Relying on subqueries instead of explicit joins can degrade a linear operation into a quadratic workload that strains production environments. This diagram shows the optimized logical processing order. This represents the data flow when every clause is positioned to maximize efficiency. SQL mastery requires more than memorizing syntax. It requires visualizing how data transforms at every stage of this physical pipeline. This UI mockup shows TBRLY. Maintaining split-second performance in a production application requires this same level of pipeline optimization, ensuring every query is evaluated in the most efficient sequence possible. Audit your own stacks against these declarative rules. Which of these semantic traps have you encountered? Let me know in the comments, and check out the TBRLY app link in the description to see how we build optimized backend architecture.